Okay, so to continue our discussion of electrons of different atoms, we're looking here at the electron distribution diagrams for elements in the first 3 rows of the periodic table. So we talked about how hydrogen, 1 proton, 1 electron to be neutral. Helium, 2 protons, 2 electrons, again, to be neutral, and so on and so forth. So what you'll notice is that we start with the electrons that have the lowest amount of energy, right? So hydrogen has that 1 electron, and so you add that first electron to the closest shell next to the atomic nucleus. And so you can see a little concentric circle in yellow, a little yellow electron there around the gray atomic nucleus for hydrogen. When you get to helium and you add this second electron can pair up and sit also in that first energy shell. Now this first energy shell is the smallest out of all the shells, and it has a very small capacity for electrons. It only fits 2. And so it's full. That's it. With helium, it's done. So by the time you get to lithium, and lithium happens to have 3 electrons, you fit the first 2 electrons in the first shell, and then you have to add a second shell in order to fit that third electron. So you can see that third electron there added in that second shell for lithium. And beryllium, 4th element, 4 protons, 4 electrons. First 2 fit in the first shell, second 2 fit in the second shell. And with each step through the periodic table of elements, you're adding 1 more electron until we get all the way to neon. Neon is our 10th element, 10 protons, 10 electrons. First 2 electrons go in the innermost shell. The remaining 8 fit in the second shell. Second shell has a maximum capacity of 8 electrons, so it's full, it's done. So if you want to add an 11th electron, as is the case with sodium, you'll have to add a third shell. So hopefully you see the trend that with each row in the periodic table of elements, we are filling the subsequent energy shell. Now each energy shell is going to have an increasing capacity. So the first shell fits 2, second shell fits 8, third shell will fit more, and so on and so forth. But the interesting thing about these shells is that every shell after the first one has this magic number. It likes to have, if it's the outermost shell, it likes to have 8 electrons in it. And when it has those 8 electrons, and if it's the outermost shell, it's happy. That atom is perfectly happy, and it actually doesn't want to react with anybody else. So helium, neon, argon, those 3 elements on the far right column of the periodic table of elements, and this goes further, right? If we go back to the full table, helium, neon, argon, krypton, xenon, and so on and so forth, these are all of your what we call noble gases. They have full outermost shells, and when we mean full, we mean either 2 for the first shell, because that's all it fits, or 8 for the rest of them. It's that magic number. This is called the octet rule. If that outermost shell has 8 electrons, that atom is happy, and it will not react under normal conditions with any other atom. So it is what we call inert. So that atom is happy, and it's going to be happy by himself, right? It doesn't want to react with anybody else. All of the other elements, on the other hand, don't have full outermost shells. And these guys want to have full outermost shells because you feel full, you're satisfied, you're happy on your own, right? If you have that full valence shell or full outermost shell, just like those noble gases on the far right side. So all the other elements are going to either take electrons, give up electrons, or share electrons so that they can look like their closest noble gas. So they can have a full valence shell. I've been using the term valence a lot. So let's introduce what that means. The valence shell is going to be the outermost shell for an atom. It can be the first shell, it can be the second shell, third shell, fourth shell, whatever it is, however big that atom is, whatever the outermost shell is, that's the valence shell. And the electrons that are hanging out in that outermost shell are called the valence electrons. And it's these electrons that are going to determine how the atom behaves chemically. Is it inert? Does it have a full valence shell and it does not want to interact with anybody else? Or does it not have a full valence shell and it wants to have a full valence shell, and so it will happily participate in chemical reactions to give, take, or share electrons? Anytime an atom gives, takes, or shares electrons with another atom, it creates a chemical bond. And so when we look at the bonding capacity of an atom, how many bonds can that atom form? What we're looking at is what we call the atom's valence, right? How many times can they share, take, or give electrons? And so let's go back to our periodic table of elements for a second. Nope, not this one. Let's do that one. So neon, right? Neon has a full valence shell. It's got 8 electrons in the second shell. It's happy. It does not want to interact with anybody else. But its next door neighbor, fluorine, there. Fluorine, this guy, you look at its valence shell, it's only got 1, 2, 3, 4, 5, 6, 7 electrons. It's missing just the one to have 8 in a full valence shell. So fluorine will very happily steal an electron from somebody else to get that full valence shell, and it has therefore a bonding capacity of 1. It'll take 1 electron. Oxygen, if you look at the valence electrons, it's got 6. It wants 8 to fill that shell, so it's going to have to get 2 more electrons. That's a bonding capacity of 2. Nitrogen needs 3 more, has a bonding capacity or valence of 3. Those are pretty easy. Let's turn to the opposite end of that same row, though. Let's take a look at lithium. Trick question. Who is lithium's closest noble gas? Oftentimes, students say it's neon just because it's in the same row, but actually helium is closer, right? Helium is the second element. Lithium is the third. They're just one door apart. And so lithium would love to look like helium. Think of it this way. Lithium only has 1 electron in its valence shell. Do you think it'd be easier for lithium to give up that 1 electron? And when it does so, there is no electron in the second shell, so the second shell does not exist. So that means the first shell is the valence shell, and that one's full. It's got 2 electrons. So do you think it's easier for lithium to give up 1 electron to get a full valence shell, or do you think it's easier for it to gain 7 electrons to fill that second shell as a valence shell? I'm hoping that you're saying it's easier just to ditch the 1, right? And in fact, lithium will do that. When it ditches the 1 electron, it has a bonding capacity of 1, giving that 1 electron away. Beryllium, again, easier to give up 2 than it is to somehow acquire 6 more, has a bonding capacity of 2. Boron, bonding capacity of 3. Then we get to carbon. Carbon's tricky. 4 valence electrons. Needs 4 more to fill the shell, or getting rid of 4. That's kind of getting rid of a lot of electrons. Don't really want to do that. Carbon's really good at sharing electrons. So it'll actually keep the 4 that it's got, and it'll share 4 more. And it has a bonding capacity, therefore, of 4 in the middle there of the periodic table of elements. All right, so we'll look at an example a little bit later, but on the third row, in the third shell, if you look at chlorine, right, chlorine in its valence shell has got 7 electrons, needs just 1 more. Sodium, on the opposite end of that third row, has only 1 valence electron, right? So these two make a really good pair. Sodium has an electron to give up. Chlorine needs 1 electron, and so sodium will give its 1 electron to chlorine. They're both going to have full valence shells. Both are going to be happy, and this is what forms sodium chloride, or table salt. All right, we talked about valence. We used our little example there of neon. Now, the last thing I'm going to mention about electrons, at least for now, is we've talked about electron shells. This is a relation to the energy level of that potential energy that electron has. One more thing to add, though, is that, yes, you can think of the electrons as orbiting the atomic nucleus in sort of that, planet orbiting the sun way, but that's not really realistic of how atoms look. And so we have to address this idea that An atom is more so the atomic nucleus in the center, and then these electrons are buzzing around all over the place in three-dimensional space, not 2D, but three-dimensional space around the atomic nucleus. And this three-dimensional space where an electron spends the majority of its time is called an orbital. Now, in chemistry, you go through the different shapes of the orbitals and the names of the orbitals and how we fill them. It's a little bit too much for us. And so I'm just going to leave you with, please understand that an orbital is simply that three-dimensional shape where an electron spends the majority of its time. And to give you an idea of what I mean by three-dimensional shape, let's take a look at our example of neon. Remember, neon has 10 protons. It's the 10th element. And so it's going to have 10 electrons. And so in the upper right-hand corner, we've got our electron distribution diagram. And so we stick the first 2 out of 10 electrons in the first shell. That one's full. And so we'll stick the remaining 8 in the second shell. That shell is also full. Neon is inert. It's one of our noble gases. Now, if we were to take that electron distribution diagram and really look at it more so as a complete atom in three-dimensional space, what kind of shape would that atom have? Well, we have to start fitting these electrons into the shape or the area, that three-dimensional space where they spend the majority of their time. And so orbitals are these spaces, right, three-dimensional spaces that each can fit only 2 electrons, right? So each orbital can only fit 2 electrons. So if each orbital only fits 2 electrons and the first energy shell only has 2 electrons, how many orbitals do you need to house those 2 electrons? Hopefully you're telling me 1. Right, and so in the first shell down at the bottom here, we can see that we only need 1 orbital, and this is a spherical orbital. So those 2 electrons in that first shell are buzzing around sort of in that spherical shape. It's pretty small around the atomic nucleus. The second energy shell has 8 electrons. If each orbital fits 2 electrons, how many orbitals do you need to house all the electrons in that second energy shell? 4. All right, so 2 electrons are going to go in a slightly larger spherical orbital. And then the remaining 6 are going to go in sort of dumbbell-shaped orbitals. So 2 are going to go in the blue dumbbell, 2 are going to go in the pink dumbbell, and 2 are going to go in the green dumbbell. So you've got 2, 4, 6 electrons here, 2 more there, that's 8, and 2 more in that first orbital for a total of 10. Now, all these orbitals, we've kind of separated them out. Remember, they're all superimposed over the atomic nucleus. So you've got the atomic nucleus in the middle, and then these yellow orbitals are where the electrons spend the majority of their time. And so the darker that yellow color, the more frequently you should expect to encounter an electron in that space. So that's kind of the three-dimensional space of an atom of neon.